Hello everybody, it's Dumplet here. Welcome to the fourth episode of Dumplet tutorial. Today's topic is on the Euclidean algorithm, which will help us get the GCD of two numbers in an easier way. Now, getting the GCD may seem trivial, as in elementary school, we're only told to factor to get the prime factorization of the two numbers, and then we're just going to take the common prime factors. Now, for example, if I want to get the GCD of 12 and 18, all I have to do is prime factorize 12 and 18. So 12 is 2 squared times 3, 18 is 2 times 3 squared, and then I'll have to do the following. I'll check each prime number or prime factor, and I'm going to take the largest power of that prime. So for example, 2 here, I'll take the largest power of 2 that is common to both. Now, the largest power of 2 that's common to both is just 2 raised to 1. Now, we go to the next prime number. Now, the next prime number here is 3. So, the largest power of 3 that is common to both 12 and 18 is 3 raised to 1. So, I'll have to write 3 raised to 1. Now, after I cover all the prime factors of these two numbers that I'm taking a GCD of, all I have to do is take the product. So, my answer should be 2 raised to 1 times 3 raised to 1. And this gives me 6. And in fact, one can verify that the GCD of 12 and 18 is indeed 6. But let us try to use the following. So let's try to use this Euclidean algorithm to help us simplify our method of getting the GCD. Now, since we're trying to get the GCD back in the days through prime factorization, so what if A and B are large? Then it's going to be more difficult. So we're going to use the Euclidean algorithm. The greatest common divisor of A and B is equal to the greatest common divisor of A and B minus A, or simply their difference. So let's do it on the example that I just showed, the GCD of 12 and 18. Now, since by the Euclidean algorithm, I can say that this is equal to the GCD of 12 and the difference, so 18 minus 12, that's 6. And compared to 12 and 18, GCD of 12 and 6 is kind of more obvious already, because that's immediately 6. Now, there's another way to say it's 6. You can say that the GCD of 12 and 6 is equal to the GCD of 12 minus 6, so 6 and then 6. So take note that it doesn't really matter which one you subtract. This is also equal to the GCD of A minus B and A. Since the order doesn't matter anyway, we're just getting the GCD of two numbers. So the GCD of 6 and 6, well, surely we can conclude it to be 6. Now, I guess it doesn't really, the use of the Euclidean algorithm doesn't really appear in examples like these, but it will in examples like these. So the GCD of 156 and 1094. Now, sure, you can use the prime factorization method, but it would be very difficult for us to prime factorize a larger number, and what more if the numbers are more bizarre and obscure. So we can use the Euclidean algorithm. Now, take note here that I only wrote that the GCD of A and B is equal to the GCD of A and their difference. But take note that I can subtract here. For example, I can subtract A a lot of times. It doesn't really matter how many times I do it. Just like in this case, I can reduce from the GCD of 12 and 18 to 12 and 6, and then make it 6 and 6, and then get the answer. So we can do the similar thing here. Now, since we want to get the GCD of 156 and 1094, well, 1094 is a little bit big, so let's try to make that small. So I can say that the GCD of 156 and 1094 is equal to the GCD of 156 and 1094 minus 156. And I can do this a lot of times. And in fact, I can do it a maximum of 7 times before the number becomes negative. So let's try to do that. So I know that this will be true, like these two will be equal via the Euclidean algorithm. And what's nice about this is that this one evaluates to 2. Now I'm going to tell you that this evaluates to 2, and so I know that the GCD of 156 and 1094 is equal to the GCD of 156 and 2. Now compare these two, which is easier to get. Is it this one or this one? Surely it's this one, the GCD of 156 and 2, because we know that this is simply equal to 2. Because, well, the GCD of any two numbers should be at most the smaller number. So since we have 2 here and 156, we know it's even, we can easily conclude it's 2. So one can use the Euclidean algorithm to help us simplify stuff. So again, let's try to do the next item, the GCD of 462 and 504. By the Euclidean algorithm, I can say that this is equal to the GCD of 504 is bigger, so let's try to make 504 smaller. So 462 and 504 minus 462 via the Euclidean algorithm. And I will tell you that this part evaluates to 42. This part evaluates to 42. Now, the GCD of 462 and 42, in fact, one can already find that 462 is actually divisible by 42, because 462 is actually 42 times 11 here. So we can say that the GCD of, 42 times 11, sorry, the GCD of 42 times 11 and 42, that's obviously equal to, that's obviously equal to 42. So that's how you can easily conclude the greatest common divisor. We can use the Euclidean algorithm to help us simplify the stuff. So like if we can simplify into something that seems obvious, like in this case, then we don't have to deal with the bigger numbers at the start, like this example and this example. So the Euclidean algorithm is just a way for you to help you simplify the getting of the greatest common divisor. Now, the Euclidean algorithm is also a very good tool in mathematical proofs. Let's just use the most famous example, the International Mathematical Olympiad, the 1951 problem 1, proving that this fraction, 21n plus 4 all over 14n plus 3, is irreducible for every natural number n. So this is already in lowest terms. So when we say a fraction is in lowest terms, then the numerator and the denominator doesn't have any common factors. So all we want to prove is that the GCD of these two numbers, so 21n plus 4 and 14n plus 3, we just want to prove that this equals 1. So let's try to see what Euclidean algorithm will tell us. So we can know that GCD of 21n plus 4 plus 14n plus 3, I can use the Euclidean algorithm. I can subtract 14n plus 3 from the bigger number, 21n plus 4. So let's get 21n plus 4 minus 14n plus 3. And this will give me 7n plus 1. And the next step, I know that I can subtract 7n plus 1 a number of times from 14n plus 3. So I'll subtract 7n plus 1 2 times from 14n plus 3, for example. So the GCD of, well, 7n plus 1 remains 7n plus 1. And if I subtract 7n plus 1 2 times from 14n plus 3, essentially I'm subtracting 14n plus 2. And 14n plus 3 minus twice of 7n plus 1, that's equal to 1. So the GCD of 7n plus 1 and 1 must be at most the smaller number, can only be at most a smaller number. So there we have it. We have the GCD of this to be 1, since the greatest common divisor must be at least 1. So we've successfully proven that this fraction over here, the numerator and denominator, has a GCD of 1, and therefore we can conclude that this fraction is irreducible. So the Euclidean algorithm, you can use it in a lot of stuff, in your simple calculations, and even in mathematical proofs. Hopefully you guys learned something new from this video, and I'll see you in the next Dumplet tutorials. Bye bye!